Hi YouTube, this is Brendan. It's going to be a video to help you with your organic chemistry course. In particular, we're going to describe how you add hydrogen halides to alkenes. We're going to discuss what controls the stereochemistry, which isn't super important here, the regiochemistry, which is extremely important here, as well as the different types of shifts that can occur that might affect the outcome of your final product. So what is hydrogen halide addition to an alkene? Well, a hydrogen halide is just a hydrogen atom and some group 7 compound, or 7A. What X can be, typically it can represent fluorine, chlorine, bromine, or iodine, although I would say most often it's chlorine and bromine. Fluorine and iodine can have kind of interesting properties and don't necessarily react the same way at the same rate. So typically it's chlorine and bromine that we emphasize here. And an alkene is just something with a CC double bond as its functional group. For these examples, what I'm going to use is this alkene right here. What this alkene is this is a 2-methyl 2-butene. This is pretty much a common one they'll use to introduce this concept because it's very easy to see the regioselectivity that takes place here. Alright, so what happens when you add a hydrogen halide to an alkene? Well, the first thing that happens is this pi bond, being nucleophilic, because it has kind of an excess of electrons, wants to come out here and grab this hydrogen. Now notice the back of the arrow goes to the pi bond, whereas the head of the arrow is attacking the hydrogen, and that's how we generally draw these arrow pushing mechanisms. And this bond right here is going to go over to the X. So what we end up with is we basically have two options that can happen. You can either think of the bond as hinging open this way, or you might think of it as hinging open this way. And in each case, we would get two different final products because we would get two different intermediates. So I'm going to show you what happens in both cases. Let's say it hinged open to the right, and the hydrogen attached on this carbon, then we would end up with a positive charge here. On the other hand, if it hinged open in the other direction, we would end up with a positive charge here as our hydrogen goes there. Now, it's very important to compare the stability of these two carbocations. Carbo as in carbon, cation as in a positively charged ion. And what we can see is that this carbocation is more stable than this one. Generally for carbocations, a tertiary carbocation is more stable than a secondary carbocation, more stable than a primary carbocation. So because this is the most stable carbocation, it has the lowest energy, which means it's going to form at a faster rate, and therefore is more likely to occur. So then what would happen next is our X minus compound, basically what was left from here, will come in and it'll attack that, and we will end up with our final product of X in that position. So X again could be chlorine or bromine. And that's it. That's basically what happens. We can get the case where it does add here. It does happen, it's just less likely to happen. And so we call these our major and our minor products. So this would be the major product, and this would be the minor product. Because the X has ended up on the more substituted reactant and the hydrogen has ended up on the less substitute reactant, we often call this Markovnikov addition. Perhaps that name's familiar to you from your organic chemistry course. All that means is it proceeds through the more stable carbocation intermediate. The H has added to the carbon that already has more hydrogens. The nucleophile of interest has added to the more substituted carbon. I think that's it. That's kind of enough of an introduction to this. In the next video, I'm going to describe what happens and what you kind of need to look for in order to see a methyl shift or a hydride shift. Thanks for watching.